the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in the binary night. No light, no face, pure sound, no sight. Stories unfold in the dark unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No mic, no fame, just the sound we crave. Tune and turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just a vibe that's real. Faceless words you can touch and feel. In shadows, voices untamed. No need for spotlight, no claim to fame. Just a beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go.
The mathematician may be compared to a designer of garments, who is utterly oblivious of the creatures whom his garments may fit. To be sure, his art originated in the necessity for clothing such creatures, but this was long ago. To this day a shape will occasionally appear which will fit into the garment as if the garment had been made for it. Then there is no end of surprise and delight. George Dantzig. George Dantzig (1914–2005) was a pioneering American mathematical scientist widely recognized as the father of linear programming. His groundbreaking work revolutionized various fields, including operations research, computer science, economics, and statistics. George Dantzig's early life was marked by a strong intellectual environment that undoubtedly shaped his future in mathematics. Born on November 8, 1914, in Portland, Oregon, he was named after the famous Irish writer George Bernard Shaw, reflecting his parents' initial hope that he would become a writer. His parents, Tobias Dantzig and Anja Aurison, were both highly educated individuals with a passion for mathematics and languages. Tobias, a Russian mathematician and linguist, and Anja, a Russian-born linguist of French-Lithuanian origin, met while studying at the Sorbonne in Paris, where Tobias had even studied under the renowned Henri Poincaré. After emigrating to the United States and initially facing financial struggles, the family eventually settled in Washington, D.C. in the early 1920s. His mother became a linguist at the Library of Congress, and his father taught mathematics at the University of Maryland. George's early academic journey wasn't without its challenges. While he initially struggled with mathematics in junior high, his father's dedication proved pivotal. Tobias Dantzig would engage his son with thousands of complex geometry problems, particularly in projective geometry, which not only nurtured George's interest but also significantly developed his analytical skills. This rigorous training program helped George excel in mathematics and science. He even assisted his father in preparing figures for Tobias's influential book, Number, The Language of Science, published in 1930. Dantzig pursued his higher education at the University of Maryland, where his father was on the faculty. He earned his Bachelor of Science degree in mathematics and physics in 1936. That same summer, he married Anne Schmuner. He then continued his studies at the University of Michigan, receiving his Master of Arts in Mathematics in 1937. Despite his strong mathematical background, Dantzig initially found abstract mathematics somewhat unappealing, preferring the practical applications of statistics. This led him to take a job as a junior statistician at the U.S. Bureau of Labor Statistics in Washington, D.C. from 1937 to 1939, working on consumer purchase behavior studies. However, his academic pursuits were far from over. In 1939, he enrolled in the doctoral program in mathematics at the University of California, Berkeley, where he would study statistics under the prominent Jerzy Niemann. It was during this period that the now famous anecdote about him solving two unsolved problems that he mistook for homework assignments occurred, a testament to his exceptional mathematical talent. Although his PhD was formally awarded in 1946, his work at Berkeley and the subsequent wartime experiences set the stage for his revolutionary contributions to linear programming. George Dantzig's truly impactful contributions emerged during and immediately following the Second World War, a period that provided him with immensely complex real-world problems demanding efficient solutions. While serving in the U.S. Army Air Force's Statistical Control Division from 1941 to 1946, he was immersed in the colossal task of planning and scheduling military operations, a process that at the time relied heavily on cumbersome manual methods. This experience highlighted for him the critical need for more sophisticated mathematical tools to optimize the allocation of vast resources like personnel, aircraft, and supplies for the war effort. The very term programming within linear programming directly reflects this military context of generating precise plans or schedules. Following the war, and after briefly concluding his PhD at Berkeley, Dantzig transitioned to the role of mathematical advisor to the U.S. Air Force, where his central challenge was to mechanize this planning process, envisioning its implementation on the nascent electronic computers. This pursuit culminated in his groundbreaking invention in 1947, the simplex method. This revolutionary algorithm provided a systematic and efficient way to solve linear programming problems, which are essentially about optimizing a linear objective like minimizing cost or maximizing output subject to various linear constraints such as limited materials or labor. Before this, finding optimal solutions to such complex problems was often a laborious trial and error endeavor. The simplex method quickly found its initial practical applications even without widespread computer availability. Famously, it was used by hand to optimize logistics for the Berlin airlift and to solve the minimum cost diet problem, demonstrating its immediate utility in real-world scenarios. His subsequent move to the Rand Corporation in 1952 was crucial for advancing the practical application of linear programming, as he focused on implementing his simplex method on the new electronic computers, thereby making it a widely accessible and powerful tool. Dantzig's influence continued to grow as he transitioned back to academia, founding and directing the Operations Research Center at the University of California, Berkeley, and later becoming a distinguished professor at Stanford University. Throughout these decades, he tirelessly refined and expanded the theory of linear programming, authored essential textbooks like Linear Programming and Extensions, and inspired countless students and researchers. His work fundamentally transformed fields ranging from transportation and manufacturing to finance and resource management, by providing a robust mathematical framework for optimizing complex decision-making processes. After laying the foundational groundwork for linear programming and the simplex method during his time with the U.S. military and at the Rand Corporation, George Dantzig embarked on a highly influential academic career that further solidified and expanded the field of operations research. In 1960, Dantzig accepted a professorship at the University of California, Berkeley, where he took a pivotal step in formalizing the burgeoning field of operations research by founding and directing the Operations Research Center. This marked a crucial shift towards establishing operations research as a distinct academic discipline. During his time at Berkeley, he continued his research into advanced topics in linear programming, constantly seeking ways to make the simplex method more efficient and applicable to even larger and more complex problems. A landmark achievement during this period was the publication of his seminal book, Linear Programming and Extensions, in 1963. This comprehensive volume became the definitive textbook for the field, widely regarded as a classic. It systematically laid out the theory, algorithms, and applications of linear programming, making the powerful techniques accessible to a global audience of students, researchers, and practitioners. This book was instrumental in disseminating his ideas and shaping the curriculum of operations research programs worldwide. In 1966, Dantzig moved to Stanford University, where he spent nearly 4 decades as a professor of operations research and computer science. His tenure at Stanford was exceptionally productive and impactful. He continued to push the boundaries of mathematical optimization, exploring areas such as decomposition methods, recognizing that real-world problems could often be too large for direct application of the simplex method. Dantzig developed and refined decomposition techniques, such as the Dantzig-Wolf decomposition. These methods break down massive linear programs into smaller, more manageable subproblems, making them solvable. This was a critical advancement for tackling industrial-scale optimization challenges. Stochastic programming, he also ventured into the realm of stochastic programming, which deals with optimization problems where some of the parameters are uncertain or probabilistic. This is vital for decision-making in environments with inherent variability, such as financial planning or resource management under fluctuating demand. Large-scale systems optimization, his research consistently focused on the optimization of large-scale systems, establishing the Systems Optimization Laboratory SOL at Stanford in 1973. This lab became a hub for developing computational methods and software routines for numerical analysis and optimization, directly addressing the growing complexity of real-world problems. Energy and economic modeling, Dantzig applied linear programming to critical societal issues, notably in the development of the pilot energy economic model. This project demonstrated how optimization techniques could be used to model and analyze national and global energy systems and their economic implications, influencing policy and planning. Even after officially retiring in 1985, Dantzig remained incredibly active in research and teaching until the late 1990s. He continued to mentor numerous doctoral students who went on to become leaders in the field, further extending his legacy. His work after 1960 solidified linear programming's place as a fundamental tool in operations research, computational science, and countless industries, illustrating its enduring power in optimizing resource allocation, scheduling, logistics, and strategic decision-making on an unprecedented scale. George Dantzig received numerous prestigious awards and honors throughout his distinguished career, recognizing his profound contributions to mathematics, operations research, and computer science. Here are some of the most notable: National Medal of Science 1975, this is the highest scientific honor bestowed by the President of the United States. Dantzig received it for inventing linear programming and discovering methods that led to wide-scale scientific and technical applications to important problems in logistics, scheduling, and network optimization, and to the use of computers in making efficient use of the mathematical theory. John von Neumann Theory Prize 1974, this highly esteemed award is given annually by the Institute for Operations Research and the Management Sciences in forms for fundamental contributions to theory in operations research and the management sciences. Dantzig was the first recipient. Harvey Prize in Science and Technology 1985, awarded by Technion, Israel Institute of Technology. This prize recognizes outstanding achievements in science and technology that have significantly advanced the well-being of humanity. National Academy of Sciences Award in Applied Mathematics and Numerical Analysis 1977, this award acknowledges outstanding contributions to the applied mathematical sciences. Harold Pender Award 1995, this award from the University of Pennsylvania recognizes individuals who have made significant contributions to engineering. Member of National Academy of Sciences, he was elected a member of this prestigious organization, which advises the nation on science and technology. Member of National Academy of Engineering, he was also elected a member of this academy, which honors individuals for outstanding contributions to engineering. Member of the American Academy of Arts and Sciences, this honorary society recognizes excellence and leadership in all fields of human endeavor. Honorary doctorates, he received several honorary degrees from various universities, including an honorary doctorate from the University of Maryland, his alma mater, in 1976. War Department Exceptional Civilian Service Medal 1944, received for his crucial work during World War II with the U.S. Army Air Forces. Linear programming is viewed as a revolutionary development giving man the ability to state general objectives and to find, by means of the simplex method, optimal policy decisions for a broad class of practical decision problems of great complexity. In the real world, planning tends to be ad hoc because of the many special interest groups with their multiple objectives. Dantzig 1983 Reminiscences about the origins of linear programming. In Mathematical Programming, the State of the Art. New York, 1983, p. 78-86. Further reading. Cottle, Richard, Johnson, Ellis, Wetz, Roger March 2007. George B. Dantzig 1914-2005 PDF. Notices of the American Mathematical Society. 54-3, 344-62. Professor George Dantzig, Linear Programming Founder turns 80 archived April 16, 2009 at the Wayback Machine, Siam News, November 1994. O'Connor, John J. Robertson, Edmund F. George Dantzig, MacTutor History of Mathematics Archive, University of St. Andrews. Dantzig, George B. 1990. The Diet Problem. Interfaces. 24, 43-7. doi 10.1287 INTE.20.4.43. JSTOR 2506139. Cottle, Richard W. 2005. George B. Dantzig, A Legendary Life in Mathematical Programming. Mathematical Programming. 105 1-8. doi 10.1007 S101007-005-0674-4. ISSN 0025-5610. S2 SID 207054446.
Mics on the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in a binary night. No light, no face, pure sound, no sight. Stories unfold in the dark, unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No light, no fame, just the sound we crave. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Hidden in shadows, voices untamed. No need for spotlight, no claim to fame. Just a beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distraction. distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go. Pure and raw. Pure and raw. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just a vibe that's real. Faceless words you can touch and feel. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just a vibe that's real. Faceless words you can touch and feel. Pure and raw. Play.